Hello students! This lesson is on piecewise functions and continuity. It is a review of some ideas from a college algebra course, as well as an introduction to some ideas about continuity that are important in calculus. This first page is review. Know the following functions and basic transformations. So our first case is y1 equals x squared. This is our parabola opening up with vertex at the origin, and in this window passes through these key points. Recall when you square negatives, you do get positives. So negative 2 squared would be positive 4, giving us this point right here. Now the next case, y2 equals x cubed. If you cube a negative, it stays negative. So some key points are these three. This graph is in the first and third quadrants and flattens out at the origin. y3 equals square root of x. Plug in 0, you get 0. Plug in 1, you get 1. Plug in 4, you get 2. This function only exists in the first quadrant, meaning you can only use non-negative inputs, and you can only produce non-negative outputs. The absolute value of x, if you plot several points, the absolute value returns a positive version of the input. So in this window, we get these key points, and we have the shape of a V with a sharp corner at the origin. And the reciprocal function. In this case here, x cannot be 0. Plugging in integers, we get some key points. And if you plug in numbers close to 0, such as 1/2, you'll get an output of 2, 1/3 output of 3, 1/4 output of 4, giving us a shape that's called a hyperbola in the first and third quadrants, and it follows the axes as asymptotes. Also, you should be comfortable with what are called transformations. If you want to shift a graph up k, then you simply add k to the rule. In function notation, you put the plus k after the f of x. Applying this to x squared, if I wanted to go up k units, I would graph x squared plus k. Applied to absolute value graph, I would add the k outside of the absolute value. Now to shift down k, we subtract k from the rule, so remove k after the function's rule. In the case of x squared would be x squared minus k. In the case of absolute value of x would be absolute value of x minus k. To shift right k, you replace all the x's with x minus k. So you do a composition, f of, and then change the x's to x minus k. So in the case of x squared, begin with x squared, delete the x, give yourself some room, and in its place, put x minus k. So the minus k is with the x inside the parentheses, is part of the base. So the square would happen afterwards. In the case of absolute value of x, begin with absolute value of x, remove the x, and in its place, put x minus k. So the minus k is inside the absolute value bars. To shift left k, we do something similar, but replace x's with x plus k. In other words, we are doing a composition f of x plus k. Begin with x squared, delete the x, give yourself some space, and in its place, put x plus k. Absolute value of x, delete x, and in its place goes x plus k. To reflect about the x-axis, you just simply multiply your rule by -1. So negate the function. Begin with x squared, multiply by -1, which means put a negative here in front. Now mind you, the order of operations here, you would still square the x first, get a result, and then do the negative second. In the case of absolute value of x, here's our rule, simply multiply by -1. To reflect around the y-axis, you replace all the x's with negative x. So you do a composition, f of negative x. So begin with x squared, delete the x, empty set of parentheses, and put negative x inside the parentheses. However, in this case, you can simplify this by squaring the negative and squaring the x separately. So this just simplifies to x squared, which is what we started with. That's because the graph of x squared is already symmetric about the y-axis. So a reflection around the y-axis will not change its nature. For absolute value of x, begin with absolute value of x, delete the x, replace it with negative x, so the negative is inside the absolute value, and you can absolute value the negative and the x separately, so this one also just simplifies back to what we started with. And again, that is because the absolute value of x is a function that's already symmetric around the y-axis. Now if you multiply a rule by k, so k times f of x, this will have the effect of doing a vertical stretch by a factor of k. So k times x squared will give us a vertical stretch of x squared by a factor of k. K times absolute value of x will do the same thing but for the absolute value of x graph. And finally, if you replace all x's with kx, in other words, you do f of kx, this will be a horizontal stretch, but by a factor of the reciprocal of k. In the case of x squared, this would look like delete the x, replace it with kx. So the k is inside the parentheses. And this would be a horizontal stretch by a factor of 1 over k. And in the case of absolute value of x, delete the x, replace it with kx, and this would be a horizontal stretch by a factor of 1 over k. If you need further review of these ideas, you will need to find supplemental materials to review this in more detail. I also recommend you experiment with these transformations using technology to become comfortable with these kinds of transformations. But this lesson will move on. Graphs can be cropped by imposing a restricted domain. Know how to do this by hand and with technology. Graph f of x equals negative 1/2 x minus 1 squared plus 3. But for x is in the interval from negative 2 exclusive to 3 inclusive, and then give the domain and range. I can see that f is the result of doing a transformation on x squared. Beginning with a graph of x squared. Next, 1/2 x squared, which is a vertical stretch by a factor of 1/2. So every point on the green curve, including these 5 key points, are now going to be half as far from the x-axis. So take this distance, cut it in half. Take this distance, cut it in half. A point on the x-axis will stay on the x-axis, and continuing, we get a flattened version. Multiply this function by negative, which will be a reflection about the x-axis. And now all the reflections and stretching have been done. Now I will do the horizontal and vertical shifts at the same time. So here we replaced x with x minus 1, and then we added 3 at the end, which gives us a horizontal shift right 1 and a vertical shift up 3. So take this red graph and go right 1 and then up 3, putting our new vertex at the point 1, 3. Now we want to crop this graph between x equals negative 2 exclusive and 3 inclusive. So I need to extend this part of the graph so I can see the point it would pass through when x is negative 2. Plug negative 2 into this function and calculate. We get negative 3 inside the parentheses. Square that, becomes positive 9 times negative 1/2 is negative 9/2, and then we'll add 3. So negative 9/2 plus 3 is negative 9/2 plus 6/2, or negative 3/2. And on this side, to confirm that we're going through the point 3, 1, calculate f of 3. 3 minus 1 is 2, square that is 4, times negative 1/2 is negative 2, and then add 3 is positive 1. And now we will crop the graph. Negative 2 should not be included, so we have a hollow point at negative 2 comma negative 3/2, and a solid point at 3, 1. And this is our cropped function. The domain of this function, we'll say capital D sub f, is precisely the restricted interval that we are given here. And the range of this function, we go as low as y-coordinate negative 3/2, excluding it, and we go as high as y-coordinate 3. Now doing this with technology, here's our function typed in and the image we get. To crop it, put curly braces to the right of the rule of the function and enter a double inequality. So negative 2 less than x less than or equal to 3. If you do a trace on this function, you will see that at the left endpoint there is a hollow, and at the right endpoint we have a solid. If you want to make those permanently visible, then type those points in as separate lines and change its formatting to be hollow and black. And you can toggle the label on, and for the right endpoint, do similar but keep it solid. Now let's go to the next page. On this page, we discuss different kinds of what are known as discontinuities. Now, a function has a jump discontinuity at a certain x value if the function approaches different y values on either side of that x value. For example, let's say we have some sort of function of x that approaches the point 1, 2, but then has a hollow point at that location. Then the function continues past x equals 1, but beginning at a different point. Now, as x approaches 1 from the left, the y-coordinates are approaching a height of 2. But as x approaches 1 from the right, the y-coordinates are getting closer to minus 1. So we see that this function has a jump discontinuity at x equals 1. Now notice currently, when x is 1, there is no defined y-coordinate. There is no solid point. You can either leave the function undefined at 1, or you could define the function at x equals 1 by putting a solid point somewhere on this vertical line, including at one of these locations, 1, 2, or 1, negative 1, or you could leave it off entirely. So regardless of whether there's a solid point on this line or where that solid point is, we still say the function has a jump discontinuity at x equals 1. Now, a function has a removable discontinuity at a certain x value if the function approaches the same y value on either side of the x value, but the function has a missing or relocated point for that x value. Consider this image. Currently, there's a jump discontinuity at x equals 2, but if you raise this portion of the function up, so as x approaches this time 2, and from the left, the function is approaching a y-coordinate of 1. This is also true as x approaches 2 from the right, still approach a y-coordinate of 1. So a removable discontinuity is a situation where a graph would be continuous but for the removal of a single point. Now that point could be defined somewhere along this vertical line, but you would not want to place it at the location of the missing point because then there will be no discontinuity. So either the point has been removed to a new location or it's been removed entirely. So either f of 2 will be non-existent or f of 2 will be some value that's not 1. And in either case, we see that f has a removable discontinuity at x equals 2. Now, a function has an infinite discontinuity at a certain x value if the y values of the function approach infinity or negative infinity on either side of the x value. Therefore, this x value would be the location of a vertical asymptote. So suppose we have a vertical asymptote at x equals -1. So on one side, perhaps the function follows the asymptote up, and on the other side, perhaps the function follows the asymptote down. Or perhaps there's only an asymptotic behavior on one side. So this is a possibility. On the left side of this asymptote, the graph goes up, but on the right side of this asymptote, the graph approaches a fixed height, and the y-coordinates do not go to negative or positive infinity. So as long as on either side of this vertical line x equals -1, you draw the function either going up to infinity or down to infinity, and then we will call this an infinite discontinuity. So as one final example, suppose the left side of the asymptote looks like this, and the right side looks like this. And there could be a dot somewhere on this line, either this location or anywhere else, or not at all. So in this case, I would say, as x approaches -1, but from the left, it appears the y-coordinates are approaching the location of this point, and let's say it's at -1, -1/2, therefore y approaches -1/2. But as x approaches -1 from the right, the y-coordinates increase without bound to infinity. And the fact that at least this or this is a positive or negative infinity means that we have an infinite discontinuity at x equals -1. All right, moving on to the next page. A piecewise function is a function that uses one or multiple rules depending on what input is being plugged in. For the piecewise function below, fill in the table, graph the function, and give its domain and range. Comment on continuity and classify any discontinuities. I'm using P to stand for piecewise function, but it really doesn't matter what letter is there. Each line corresponds to a different piece of a different function, all put together into one function. First, notice these intervals over here. These are the conditions on x which will dictate which rule we use to find the output. Notice that there is no overlap in these sets. They are all disjoint. If x is in this first interval, then we use this rule to get the output. In other words, the output will be 2. If x is in this interval, we plug those x-coordinates into this rule, which is a linear function. If x is 1, we simply get an output of 4. And if x is in this interval here, we plug into this transformed graph of 1 over x. So looking here in our table, when x is -4, notice -4 is not an element of any of these intervals. Therefore, this function will have no output. So we say D and E or does not exist. However, -3 is in the orange interval because it's the left endpoint, which is included because of the bracket. And this function says that when x is in the orange interval, then the output should be 2. Now, -2.1 is also in the orange interval. So again, the output will be a 2. Now, -2 is not in any intervals. It's not in the orange or green because -2 is not included in either. So this function has no output. -1 is in the green interval. So plug -1 into this line, and we get 2/3 plus 2, which is 8/3. 0 is also in the green interval. So plug 0 into the line, and we get a simple 2. 1 satisfies the blue condition, so the output will be 4. 2 satisfies the red condition. It's in the red interval. So plug 2 into that rule of the function, and we get -1 back. And 3 is not in any of the intervals, so we have no output. Now I could start plotting some of these points into our graph, but I'll take a different approach in producing the entire graph of this piecewise function. Looking at the orange rule, y equals 2, I'll graph it in its entirety. But now we're going to crop it from x equals -3, inclusive, to x equals -2, exclusive, and keep only that portion in between. Now the green rule is going to be a line with y-intercept 2 and slope of -2/3. So right 3, down 2. But we're now going to crop it from -2 exclusive to +1 exclusive, meaning use hollow endpoints and keep only the portion in between. Now the blue rule gives us a single point when x is 1 and y is 4. And now the red rule, this is a transformation of 1 over x. 1 over x has been reflected across the x-axis and then shifted right 1. This is the red graph in its entirety, but now we want to crop it and keep only those x-coordinates that are to the right of the asymptote up to x-coordinate 2, and get rid of the rest. Now let's find the coordinates of all these hollow and solid points. The orange ones are easy to find. Now let's find the green hollow endpoints. Plug -2 into the green rule. That gives me 4/3 plus 2, which is 10/3. Now plug 1 into the green rule. That gives me 2 minus 2/3, which is 4/3. Of course, the blue point is at 1, 4. And this red solid point we already found down here in our table. It's 2, negative 1. Now let's find the domain of this function. The domain will simply be the union of all of these intervals we have over here. So let's begin with the orange interval. Now this function was never defined when x was negative 2. So negative 2 must be excluded from our domain. So we'll do a union, pick up on the other side of negative 2. And then every x coordinate past negative 2 is included in the domain, including when we transition to the blue and then transition to the red. All x coordinates are accounted for up to x equals 2, and then past 2, the function is no longer defined. So the union of these three sets, the green, the blue, and the red, can be condensed into a single interval from negative 2 exclusive up to 2 inclusive. Now the range will be the y-coordinates. Every y-coordinate from negative infinity up to a y-coordinate of negative 1 is in the range. Then these y-coordinates are not included. And then we start to get inclusion again, beginning with 4/3 but not including it. And these y-coordinates are all in the range up until this green hollow point. Don't include that y-coordinate. But then there's one more y-coordinate possible, and that's at height 4. So our y-coordinates, starting with negative infinity up to negative 1, inclusive, union. The range of the green will enclose the range of the orange, and that range is 4/3 up to 10/3, exclusive. And then we have one more y-coordinate, a single number 4, which I'll put in curly braces. So these are all the possible y-coordinates. This interval includes the range of the green portion as well as the orange. Now a comment on continuity and classify any discontinuities. To be continuous means you can draw the function as x varies without needing to lift your pencil. So this little orange segment is considered a continuous portion. This green segment is considered a continuous portion, and this red portion is considered continuous. We don't really say that a single point is continuous though, but the discontinuities occur at a few key values. So notice at x equals negative 2, one side of the graph approaches a height of 2, and the other side of the graph approaches a height of 10/3. This is what we were calling a jump discontinuity. So it's as if the y-coordinates, as soon as we get to x equals negative 2, they jump to a new height and continue. So P has a jump discontinuity at x equals negative 2. Now we have another discontinuity when x is 1. But notice on the right side of x equals 1, we have a function approaching negative infinity. So because on one side of this x value we have y-coordinates approaching either positive or negative infinity, we call this one an infinite discontinuity at this location. So P has an infinite discontinuity at x equals 1. Okay, next page. Determine the rule for the piecewise function depicted below. Give the domain and range. Comment on continuity and classify any discontinuities. I'm going to color coordinate. So I have a green portion, an orange portion, a blue portion, and a red portion. Each of these will require its own rule. For the green portion, let's go ahead and assume that the graph continues off to the left. It has not been cropped on the left side. But notice we do have a hollow point here when x is negative 3. Also, it appears that this is a transformation of the square root of x. Now, normally the square root of x is this pink graph. It begins on a solid point at the origin, and it contains the point 1, 1. So in my mind, I'm imagining beginning with the square root of x. I'm going to reflect this across the y-axis by replacing x with negative x. Now notice the pink, currently, if I go left 1, I go up 1. But the green, from its point of origin, goes left 1 and up 2. So there's a vertical stretch involved. So now I'm going to double this function. Now I'm going to take the pink graph and shift it left 3 and down 1. So to go to left 3, we're going to replace x with x plus 3, and that radical goes over all that. And then the down 1 is putting a minus 1 at the end, outside of the radical. And this makes our green function. Now the orange function is just a horizontal line at height 4. So that rule will just be 4. Now the blue function is a line that goes through 2 points, the point 1, 2, and the point negative 2, 4. If you recall from algebra, we can find the slope of this line by doing the difference of the y-coordinates over the difference of the x-coordinates. That gives me negative 2/3, confirming that if I go right 3 from one point, I would need to go down 2 to get back to the line. Then I can use point-slope form to construct the equation of this line, and let's use the point 1, 2. So y minus the y-coordinate of that point is equal to the slope times x minus the x-coordinate of that point. So simplifying a little bit, we get negative 2/3 x plus 2/3, and then add the 2, giving us y equals negative 2/3 x plus 8/3. Now the red portion looks like a transformed version of x squared. So here's x squared. Notice if you go right 1, you would go up 1 to get back to this. But for the red graph, if you start at the vertex and go right 1, we only go up 1/2. So a vertical stretch by a factor of 1/2. And now we want to shift this graph right 3 and up 1. So to shift right 3, change x to x minus 3, and then up 1. And that makes our red function. So our overall function is equal to, put all 4 of these pieces together, and now we just got to crop them appropriately. So the green function is true only if x is strictly less than -3. Or you can say x is an element from -infinity up to -3. And exclude the -3 because we have a hollow endpoint here. And I will use interval notation moving forward. Now y equals 4 if x is between -3 and -2. Include the -3, but exclude the -2 because we have a solid on the left but a hollow on the right. Now we'll crop the blue portion, so x is between -2 and 1. Exclude the -2 but include the 1. Again, because we have a hollow on the left side of the blue but a solid on the right side of the blue. Then notice we have a gap of x coordinates, and we don't pick up the function again until we get to x equals 2 exclusive. So the red portion of the graph is drawn for x is between 2 and 5 exclusive of both endpoints. And here's our piecewise function. Now we'll comment on any discontinuities. At x equals -3, we have a discontinuity. The graph approaches a height of -1 from the left and a height of +4 from the right. No infinities are involved here, and the two heights are different, therefore this is a jump discontinuity. At x equals -3. At x equals -2, if it weren't for that hollow point, we would be able to draw from the orange to the blue in a continuous fashion without lifting our pencil. But because a point has been removed from an otherwise continuous graph, then we say that we have a removable discontinuity at x equals -2. Both the orange and the blue are approaching a height of 4 as x gets closer to -2 from both sides. So f of x has a removable discontinuity at x equals -2. Now we only classify discontinuities at singular values of x. So because we have a gap of x coordinates here, we don't really classify this as a discontinuity at a single value of x. So the only two singular locations where a discontinuity occurred were at x equals -3 and at -2. And in the end, this graph is composed of 4 continuous pieces. Individually, the green, the orange, the blue, and the red are all continuous over their respective domains. And backtracking to give the domain and range, the domain will be the union of these intervals. Well, these two intervals stitched together form one continuous interval from -infinity up to -2. These two intervals cannot be stitched together into one interval because -2 is missing from both. So we need a union from -2 up to 1 inclusive, and then these two intervals cannot be stitched together at all because of this gap between the blue and the red. And now the range, the lowest y coordinate is down here, -1, but exclusive. And because the square root function goes up forever, the green portion will have y coordinates that go up to +infinity. That'll include all the possible y coordinates that we could get from these other three portions. So the range will be -1, the lowest y coordinate, exclusive, up to infinity. Next slide. The absolute value function can be expressed as a piecewise function. Graph each function below, comment on continuity, and classify any discontinuities. So here's a graph of the absolute value of x with a sharp corner at the origin. You can think of this as a right and left side and define this in a piecewise manner. So the blue function is simply y equals x, and we graph this for x being positive. The red graph is the graph y equals -x, and we graph that for when x is negative. Notice currently 0 is not accounted for because both of these inequalities are strict. You can include the origin, the point 0, 0, with either the blue definition or the red definition. Include it with the blue definition, you would put a partial equal sign, which would effectively make the origin be part of the blue curve. Or you can include it with the red definition and technically make the origin part of the red curve. Or you can define it separately. Say that when x is 0, just give 0 back. Any of these are acceptable. Now observe the following. If you begin with a positive input, then the absolute value does nothing to it. That's why you can simply remove them. But if you begin with a negative input, then the absolute value of that negative number will change it back to a positive. Well, another way to do that is to negate that negative number. So if you try to plug in x equals 5, 5 is positive, plug in 5 here and you get 5 back. But if you try to plug in -3, negative 3 is in this red interval. So you plug negative 3 into this function and you get negative 3, which is positive 3, which is exactly what the absolute value returns. And then if you try to plug in 0, you get 0 back. Finally, observe that f of x is continuous. Even if you break it down into 3 pieces like this, when you put all those pieces together, I get a function that I can draw and transition without ever lifting my pencil. So this has no discontinuities. Let's look at g of x next. If x is positive, then the absolute value of x is just x, which is over an x, and we get just 1. If x is negative, then the absolute value of x becomes negative x over an x, which is negative 1. And if x is 0, well, in this case, I can't plug in 0 because I would get 0 over 0. So this has no output. Now let's think about this before I graph. Pick any positive x coordinate, like 3. Plug it into this function. We'd get absolute value of 3 over 3. Well, that would just be 3 over 3, which is just 1. Plug in a negative x coordinate, such as negative 5. Plug negative 5 into this function. Absolute value of negative 5 is 5 over a negative 5, and that's going to simplify to negative 1. So this graph winds up producing the following image. We graph y equals 1 if x is positive and have a hollow point where it hits the y-axis. And then we graph negative 1 if x is negative and have a hollow point on that y-axis. And there would be no solid point anywhere on the y-axis. So here we have a jump discontinuity at x equals 0. Now let's look at h of x. Let's first consider the graph of x squared minus 2x without absolute values on it. First factor out in x, set y equal to 0 and solve, and you get 2 solutions. These are the 2 x-intercepts. Also, this graph is a parabola opening up, and there's symmetry with the parabola, so the vertex must be when x is 1, halfway between the intercepts. And when x is 1, plug that in, we get negative 1 back as the y-coordinate. So here's a graph of y equals x squared minus 2x. When you now do the absolute value of this function, any portions of the curve where the outputs are negative, so this portion right here, will be turned into a positive output instead, in other words, reflected across the x-axis. So part of the graph was reflected and part of it was not. So we can define this as a piecewise function. Let's do the green part first. The absolute value bars were not necessary, in other words, you can remove them, for x in the interval from negative infinity to 0, union 2 up to infinity. The red portion is the same graph but reflected, so it's the negative of x squared minus 2x using parentheses if x is between these x-intercepts, so in the interval from 0 to 2. And then like we did over here, let's go ahead and define what happens at the x-intercepts. We will say that this function produces 0 if x is 0 or 2. And then finally, m of x. If x is anywhere in this union of green intervals, then I can remove the absolute value, resulting in a function divided by itself, which will be just 1. If x is in the red interval, then removing the absolute values would require a negative sign to precede this function, and then over itself, which simplifies to negative 1. Now, if x is 0 or 2, that'll cause the denominator to be 0, and we cannot divide by 0, so this piecewise function yields no output. And now we simply have to graph y equals 1 and y equals negative 1 for these correct intervals. Here's y equals 1 in its entirety. Now let's crop it with hollow endpoints and keep only the left and right sides. Now we graph y equals negative 1 in its entirety, crop it at 0 and 2, and keep only between these hollow points. Now discussing continuity, h has no discontinuities, but m has jump discontinuities at x equals 0 and at x equals 2. All right, and this concludes our lesson on piecewise functions and continuity.